Okay, welcome. Very short video. We are attempting to prove a very simple low-level number fact, which is that for a positive integer n, that n cubed is always less than 3 to the n. So this is the kind of thing that you can prove by induction, using even more sort of basic low-level properties of inequalities and numbers and stuff. So in class, at the last 5 minutes of class, we first did a little bit of experimentation to convince ourselves that this theorem is true. And though it seems like exponentials are always so much bigger than any polynomial expression, yeah, that's true eventually, but maybe not sort of immediately. And in fact, we see when filling out this chart that in the comparison between n cubed and 3 to the n, that 3 to the n indeed starts out bigger, but they're sort of like tied for a second at n cubed. And in fact, if you graph these two functions, you will see that they intersect each other twice. Once at this integer 3, and again at some other point. But then beyond 3, seemingly the exponential function just keeps growing faster and faster and leaving the n cubed function behind. So now, by filling out this chart and sort of thinking about it, I'm now convinced that this is true, starting at 4. So for n greater than 3. Okay, so now I'm ready to prove the theorem. How? What we did in class was we said, okay, I'm going to do this by induction. Let's do the base case. Our base case is n equals 4. So base case n equals 4, and I've already established that it's true for 4. So great. Now all I have to do is the inductive step, and in the inductive step I'm going to start with the property being true for n and show that the property is true for n plus 1. And so I assume this and I try to show this. How can I show this? This is what's quite hard. Is the whole goal now is to prove this step with a star in front of it. Well, my strategy, as I explained in class, was to rewrite this thing that we're trying to prove ever so slightly, and just apply an exponent rule that 3 to the n plus 1 is just 3 times 3 to the n. And if I divide both sides by 3, which is of course equivalent, all these 3 steps are equivalent to each other, then I arrive at this kind of purple boxed statement. And this statement in the purple box is basically the thing I'm trying to show, and yet it has the advantage of looking a lot like my inductive hypothesis. And at this moment I go into a deep think and come up with this statement right here, that n plus 1 cubed over 3 is less than n cubed. I wish that this were true, because if this were true, then I would know that n plus 1 cubed over 3 is less than n cubed, which is in turn less than 3 to the n, which gives me by transitivity the thing in the purple box, which is the thing that I need. So now I can just set my mind to proving this thing in the blue box. How? By working backwards. And I keep, so I write it out, I multiply both sides by 3, I expand all this out, I subtract n cubed from both sides. Then I just tried some stuff. Okay, so I have some experience with this, so I just kind of knew what to do a little bit maybe. I moved everything over to one side except for the 1, because I kind of wanted to factor, and it seems easier to show that this expression is bigger than 1. Is it always bigger than 1, that left-hand side? Well, you can kind of like try some stuff, right? Like you can try like n equals, I don't know, 1 for example. Well, when n equals 1, it's not true. But when n equals 2, I think it's like already true, right? That 8 minus 6 minus 3, no. But it doesn't need to be true for n equals 1 and 2. It needs to be true for starting at 4. So alright, let's just go straight to 4. When I go straight to 4, then that's like 16 times 2. That's 32 minus 12 minus 3. That is bigger than 1. So what I'm doing here is I'm playing around and I'm convincing myself that this is true. Because now the quadratic is just going to keep growing faster and faster than the linear. And so now I did something kind of very smooth in between this line and this line. This was happening just as class was ending. I said that, well, since I know that n is bigger than 3, then I know that n is bigger than 1. And so to show that this product is bigger than 1, let me just show that they're both bigger than 1, and the product of two things that are each bigger than 1 is bigger than 1. Therefore, my problem reduces to showing that this is bigger than 1. And now I moved it a little bit more, and now here's where it's sort of the class ended, so let's finish it off. I need to show that 2n squared is bigger than 3n plus 4. And here's the thing, I want to factor again. This just feels like this should be true, right? Because, like, come on. If I multiply an n by a 2, what is this? This is ultimately like, you know, kind of like 3 times n or something like that. Alright, so here is where I shall use, I'm going to do another smooth thing, which is instead I'm going to show that 2n squared is bigger than 3n plus 6. Why should I do that? Because that is equivalent to showing that 2n squared is bigger than 3 times n plus 2. Okay, is that true? I feel like I lost my whole train of thought here. Oh no, here we go. So now I know that n is bigger than 3. So once again, it suffices to show that 2n is bigger than n plus 2. Because if I can show that 2n is bigger than n plus 2, then I can just multiply both sides by my n is greater than 3 fact. Is this true? Yes, because n is greater than 2. Alright, so what just happened? What just happened was I would call it a cacophony of scratch work that was extremely difficult to follow, involving a lot of like hunches and like weird stuff. That's why it's important in these kind of proofs to then go back and do it for real. So now I'm going to go back and do it for real, and I would never think to be able to do this proof if I hadn't already done the scratch work, but the proof itself should be extremely clear. Okay, here we go. I shall now prove the wish. How? By following the logic kind of all the way back up. And so this is what I'm going to do. I'm going to start with the fact that n is bigger than 3, which is kind of part of my inductive hypothesis, essentially. I'm supposing that this is true, you know, sort of for some arbitrary n greater than 3 is really the full statement of my inductive hypothesis. Okay, well, if n is greater than 3, it's certainly true that n is greater than 2, because anything greater than 3 is also greater than 2. Well, now I shall add n to both sides of this, so then that gives me 2n is greater than n plus 2. But it's also true that n is greater than 3. And so now multiplying these two inequalities, which is a completely legitimate thing, gives me 2n squared is bigger than 3n plus 2. So that means that 2n squared is bigger than 3n plus 6. And that means that 2n squared minus 3n is bigger than 6. But if 2n squared minus 3n is bigger than 6, then it must be true that 2n squared minus 3n is bigger than 4. Because anything that's bigger than 6 is also bigger than 4. Now I subtract 3 from both sides of this, so that gives me 2n squared minus 3n minus 3 is bigger than 1. Now we're getting somewhere, right? Now I do another move. I say, okay, hey, by the way, don't forget that n is bigger than 3. Since n is bigger than 3, maybe I'll do it up here. Since n is bigger than 3, then it follows that n is bigger than 1, because anything bigger than 3 is also bigger than 1. And now once again, I combine these two inequalities into n times 2n squared minus 3n minus 3 is bigger than 1. Which is kind of like what I wanted, right? So now that is 3n cubed minus 3n squared minus 3n is bigger than 1. Where is that? No, that should be a 2, sorry. 2n cubed minus 3n squared minus 3n is bigger than 1. Now I move all that stuff over, so 2n cubed is bigger than 3n squared plus 3n plus 1. Now I add n cubed to both sides of that, so that gives me 3n cubed is bigger than n cubed plus 3n squared plus 3n plus 1. So that shows that 3n cubed is bigger than n plus 1 cubed. Almost there. And so, flipping this inequality, that means that n plus 1 cubed is less than 3n cubed. And if I just divide by 3, I have now proven the wish. And that's what I wished to prove. Why did I wish to prove that? Because I also know that n cubed is less than 3 to the n. That is my inductive hypothesis. And now I combine these two, I combine these two, but not in a multiplication way, in a transitive property way. So I have that n plus 1 cubed over 3 is less than n cubed, which is in turn less than 3 to the n. And therefore, n plus 1 cubed over 3 is less than 3 to the n. And therefore, by multiplying both sides by 3, I get that this is 3 to the n plus 1. And this is exactly the fact that I needed. It shows that this property has been inherited. And so, oops, sorry about that, that was very loud. So in my opinion, this is now just my sort of aesthetic opinion, is that the clearest way to prove these kind of things is by working backwards, but then sort of writing out. I think it's especially important for people to be able to follow your logic, that you then sort of rewrite the whole proof out in a kind of linear, careful manner in which every line follows from the previous one. And in this case, I'm just using the simple fact that n is bigger than 3 to prove a simple fact about numbers. I put a blue box around sort of the leaves of my tree, so to speak. Here I just applied like the fact that I can multiply two inequalities together. That is to say that if everything is positive, that when a is less than b and c is less than d, therefore AC is less than BD. That's just fact of numbers that can also be proven, but we're not going to do that. Here I applied that same multiplicative principle again, and here I just applied the transitivity of the less than relation on numbers, and so that sort of makes clear kind of what went into this proof. Okay, so the point of this was not necessarily to do it. The point of this was to sort of live the strategy. When you have something really hard that you're trying to prove, especially in inequality, it's this no need wish model. I think is very helpful. And then the hard part becomes just the algebra. But the algebra of polynomials, should be doable. And there might even be a smoother way of doing this. There might even be a way of doing this that's much easier than what I came up with. This is just what I came up with. Okay, goodbye, Internet.